In this video, we'll be talking about polynomial functions and their graphs. A polynomial function of degree n is a function of the form p of x is equal to a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1 power plus plus a sub 1 times x plus a sub 0, where n is a non-negative integer and a sub n does not equal 0. The numbers a sub n minus 1, a sub 2, a sub 1, and a sub 0, these are called coefficients of the polynomial. The number a sub 0 is called the constant term or constant coefficient. A sub n is called the leading coefficient, and a sub n times x to the nth power is called the leading term. That was a lot, so let's look at some examples so that we can see how these work. Example 1 asks us to fill out the table below. The first example of our polynomial is p of x is equal to negative 2. This is known as a constant polynomial because we just have a constant or a number. Now, the degree, remember, is the highest power that's on x, and notice that there's no x there because I can write this as x to the 0 power, and remember x to the 0 power is equal to 1, so I can also remove that. So in this case, the degree is 0, our leading term is negative 2, and our constant term is also negative 2, since that's the only term that's there. The next example, p of x is equal to 2/3 x minus 9, is an example of a linear polynomial. Now, the power on x here is 1, so this is a degree 1 polynomial, which again is a linear polynomial. The leading term is 2/3 x, and the constant term would be negative 9 here. Now, in our previous video, we talked about a polynomial of the form ax squared plus bx plus c. That is also known as a quadratic polynomial, and a quadratic has degree 2. In this case, our leading term is negative x squared, and our constant term is negative 11. I'm going to go ahead and continue filling out this table. So in the last two rows, we have a cubic polynomial and a quartic polynomial. A cubic polynomial is a polynomial that has degree 3, and a quartic has degree 4, and the leading terms and the constant terms are there in the table. Polynomials are continuous, which means that there are no holes or breaks when graphing a polynomial function. The domain of a polynomial is always going to be all real numbers unless the domain is restricted. A more intuitive definition for continuous is, if you're drawing the function's graph, you don't need to pick up your pen or pencil to draw the graph in its entirety. So here, in this first graph, if I trace this, I don't need to pick up my pen or pencil in order to draw the graph in its entirety, but in this second graph, I would need to lift my pen or pencil and then continue on, and because there's a break, in this second graph, it is not continuous. But again, polynomials are always continuous unless we restrict the domain. Now, end behavior is a description of what happens to the output values or the y values of a function as the input values or the x values approach infinity or negative infinity. In this case, because my function is going in these directions both ways, so I have these arrowheads, and suppose this function was called f of x. If I wanted to describe the end behavior of this function here, I would say as x approaches infinity, that means that the x values are getting larger, so we're going to the right and we're going this direction. What's happening is the y values are going up towards infinity. So we have this arrowhead here, and we say as x goes to infinity, f of x goes to infinity. And then we also want to see what happens to the left. So let's say I'm looking and plugging in numbers into my function that are going towards negative infinity. So then another statement we can make and say is as x approaches negative infinity, f of x also approaches negative infinity. Now, end behavior is going to vary for different polynomials. Let's see some more examples. Example 2 says describe the end behavior of the following polynomials. In part A, we have f of x equals x squared. Now, if I were to sketch a graph of this, f of x equals x squared is a parabola that has its vertex at the origin. Here's my y-axis, and here's my x-axis. Now, the end behavior for this, as x approaches infinity, f of x approaches infinity as well, because in this function, if I plug in really large positive numbers, my output values are also going to be very large positive numbers. Now, as x approaches negative infinity, so if I were to plug in something like negative 100 or negative 1000, because I'm squaring it, the output value is going to end up being positive. So f of x also approaches positive infinity, even though we're plugging in negative numbers that are very large. So these here represent our end behavior for the function f of x equals x squared. Let's move on to part B. If I were to sketch a graph of this function, here's my y-axis, here's my x-axis, and my cubic function is going to look something like that. And for this one, we would say as x approaches infinity, g of x approaches infinity, because if we plug in a really large positive number, our output will be positive. And then we can say as x approaches negative infinity, g of x also approaches negative infinity. So this looks very similar to the one we did on the previous page, and here is our end behavior. In part C, we have h of x is equal to negative x to the fourth power plus 5x plus 2. Now, I don't know exactly what the graph of this function looks like. However, it turns out that these smaller powered or degree terms, because their exponents are smaller than 4, they don't really end up making a huge difference when it comes to the end behavior, because ultimately we're plugging in really large numbers for x, and definitely the constant term. If I plugged in like a billion, adding 2 to it isn't going to make a huge difference, and adding 5x, even though that will be a large number, negative x to the fourth power is going to be a much more high magnitude number and will affect the overall output more. So it turns out that we can ignore these lower degree terms, and our focus is really on negative x to the fourth power. Now, because we're only focusing on the leading term, we want to then focus on two things. We want to focus on the degree, which in this case is 4, and we also want to think about the leading coefficient, which is negative 1. So if I just had x to the fourth power, regardless of whether I plug in a positive number or a negative number, that's going to end up being positive. But then if I end up multiplying it by negative 1, which is our leading coefficient, that's going to turn all of our output values negative. So all of that is to say, for h of x, as x approaches infinity, our output, h of x, will approach negative infinity. And then as x approaches negative infinity, h of x will also approach negative infinity. So I don't know what's happening near the middle of the graph, but the end behavior, if I were to think about what it looked like, I know that it's going to look something like this down here, and then on this side, it's going to look something like that down there. And again, I don't know quite what's happening in the middle, but this is called end behavior because I'm looking at the ends. And on the ends of my graph, both ends are going downwards. So it turns out that there are really only 4 cases when you look at the leading term. And the first thing we said we looked at was the degree. So if the degree is even and the leading coefficient is positive, what that means is the end behaviors on both sides are going to be going upwards. And so we write that as x goes to negative infinity, f goes to positive infinity, and as x goes to positive infinity, f goes to positive infinity. Let's go ahead and fill in the rest of this table. If our degree is even and our leading coefficient is negative, which is like the example we just saw, y equals negative x to the fourth power, then we would say as x approaches negative infinity, then f approaches negative infinity. As x approaches positive infinity, f would approach negative infinity. So in our next case, if the degree is odd and the leading coefficient is positive, an example of that would be something like y equals x cubed, which we saw in the previous example. Then we would say as x approaches negative infinity, f approaches negative infinity. As x approaches positive infinity, f approaches positive infinity. Now, the last case is if the degree is odd and the leading coefficient is negative, and that would be something like y equals negative x cubed. And in this scenario, we would say as x approaches negative infinity, f would approach positive infinity, and as x approaches positive infinity, f would approach negative infinity. Now, this is a lot to write in terms of the end behavior, and if you're in my class, this isn't a super common notation, but when I ask for end behavior, I'm okay with you using arrows, and the arrows that I'm referring to are these arrows here. So if you have any of these cases, then you can use these arrows to denote the end behavior. So again, if I ask you for end behavior, you can do up, up, down, 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 up, or up, down. So these are the 4 variations on the arrow notation that talks about end behavior. Example 3 wants us to determine the end behavior of f of x equals negative 3x squared plus 4x to the 5th power minus 7x to the 9th power. Now, something that you want to be careful of is here, the terms are not in order of their degrees going from highest to lowest. So the leading term is actually this one because that's the one that has the highest power. So now that we've identified the leading term, we see that the leading coefficient is negative 7, which is negative, and our degree is odd. So going back up to our table, we have this case where our degree is odd and our leading coefficient is negative. So that's going to mean our end behavior for this polynomial is going to be up, down. And again, if you don't use the arrow notation, then we would say as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches positive infinity. So there's our answer. Now, real zeros of polynomials. If p of x is a polynomial and c is a real number, then the following statements are equivalent. The first statement says c is a zero or root of p of x. 2 says x equals c is a solution of the equation p of x equals 0. 3 says x minus c is a factor of p of x. And 4 says c comma 0 is an x-intercept of p of x. Let's see this 4 statements in action. So let's say I had a polynomial p of x equals x squared minus 7x plus 10. So the first statement says c is a 0 or root of p of x. And it turns out that we can factor this into x minus 5 times x minus 2. And so if I were to use the zero product principle and solve for the zeros or the roots, I'd get 5 and 2. So let's just work with 5 for now. So if I wanted to write the first statement, I could say 5 is a 0 or root of this polynomial p of x. The second statement is I could say x equals 5 is a solution of the equation x squared minus 7x plus 10 is equal to 0. Okay, the third statement is I could write that x minus 5 is a factor of p of x. As we can see here, we factored it, and here is one of the factors. So that's the third statement. And then the fourth statement, we can say 5, 0 is an x-intercept of p of x. So those are those four kind of equivalent or similar statements. This is called the intermediate value theorem for polynomials, and it says if p of x is a polynomial and p of a and p of b have opposite signs, in other words, one of them is negative and one of them is positive, then there exists at least one value c between x equals a and x equals b such that p of c is equal to 0. Now, what does that exactly mean? So on the right here, we have a comma f of a, so that's an ordered pair here, and b comma f of b, that is an ordered pair here. Because the function that we're looking at is a polynomial, it must be the case that we have to connect these two ordered pairs, and because polynomials are always continuous, there's no way that we can get from one point to the other without having to cross the x-axis somewhere. Now, we don't know exactly where, except for it has to be somewhere between x equals a and x equals b, but somewhere between there we have this value c, such that when we plug c into our function, our output ends up equaling 0. And again, that has to do with the fact that polynomials are always continuous, and we have to meet the condition that they have opposite signs. In other words, one of the values is negative and one of the values is positive. Example 4 says, show that the polynomial p of x equals x to the fifth minus 3x squared minus 1 has a 0 between x equals 0 and x equals 2. So what we need to do is we need to plug in x equals 0 and x equals 2 into our function so that we can meet the condition. So let's evaluate p of 0 first. If we plug that in, we'll get 0 to the fifth power minus 3 times 0 squared minus 1, and if you go about simplifying, that's going to end up equaling negative 1. If we evaluate p of 2, that is going to be 2 to the fifth power minus 3 times 2 squared minus 1. 2 to the fifth power is 32 minus 3 times 4 is 12, and then minus 1, so that's going to be 19. So notice that one of our output values is negative and one of our output values is positive. So we've met this condition that they have opposite signs. We also need to meet the condition that the function that we're looking at is a polynomial, which it is, because we're looking at this and it's of the form p of x equals a sub n x to the nth power plus a sub n minus 1 x to the nth minus 1 plus dot 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 plus a sub 1 x plus a sub 0. So because it's in that form, it qualifies as a polynomial, and therefore we have met the conditions of the intermediate value theorem for polynomials. Because we have met the conditions, then we can make our conclusion based off the theorem, which says then there exists at least one value c between x equals a and x equals b such that p of c is equal to 0. So let's go ahead and write up an argument or a mathematical proof now. All right, so I started writing our proof, which says p of 0 is equal to negative 1, which is negative, and p of 2 is equal to 19, which is positive. So they have opposite signs. By definition, p of x is a polynomial. Therefore, by the intermediate value theorem for polynomials, I went ahead and I abbreviated that because it's very long to write out. So I abbreviated to IVTP. P of x must have a 0 between x equals 0 and x equals 2. So now that we've finished our mathematical proof, we typically end it with some some kind of symbol. The most common symbol is a square like this. That is like a mathematical period that tells us that our proof is done. This is typically the symbol that I use to notate that I have finished a mathematical proof. Now, let's just quickly recap. When you are doing a mathematical proof, you need to make sure that the conditions of the theorem that you're using are satisfied, which we've done. So we've mentioned that they have opposite signs, because this one is negative, this one's positive, so they have opposite signs. And we also mentioned that p of x is a polynomial. So we've explicitly shown that our two conditions for this theorem are met. I also need to name drop the theorem, which I did. I explicitly cited the intermediate value theorem for polynomials. And then I need to state the conclusion, which is this last part here. So those are the nice pieces that we have together for our mathematical proof. Example 5 says, let p of x equal x cubed minus 2x squared minus 3x. Find the zeros of p of x and then sketch a graph. Now notice that in p of x, every term has an x in it. So it turns out that I can factor out an x, and I'd be left with x squared minus 2x minus 3. Now, the thing that's left over in the parentheses is a quadratic, and it's one that's nicely factorable. So I have x, and then my quadratic inside the parentheses will factor into x minus 3 times x plus 1. Now, I want to find the zeros, so what I'm going to do is I'm going to set this equal to 0 and use the zero product principle. The zero product principle tells us that we should set each of our factors equal to 0, and then we can solve for x. So this is already solved for us. We get x equals 0, x equals 3, and x equals negative 1. So here are our zeros. And now that's going to help us graph because those help us find the x-intercepts. So one of our x-intercepts is here at 0, 0. One of them is here at 3, 0, and one of them is at negative 1, 0. Now, the other thing that will help us in terms of graphing is looking at the leading term, which is x cubed. So that means that the end behavior, because our leading coefficient is 1, and that's positive, and then our degree is odd, that means our end behavior is going to look like this, down, up. So I'm going to go ahead and basically copy those arrows onto my graph. And now I don't know exactly what's going to happen in the middle stuff, but I do know that my end behavior looks like that, and it has to go through these x-intercepts. So maybe it's going to look something like that. Now, that might not be terribly accurate, but again, we have our x-intercepts, our graph is going through those x-intercepts, and we have the end behavior. Let's just use a graphing utility to make sure that we graphed this at least somewhat accurately, or that we got the end behavior and the x-intercepts correct. So if you click y equals, and then we can go ahead and enter in our function. So I'm going to do x cubed minus 2x squared minus 3x. And after I've entered in my function, I can go ahead and click graph. Now my window might not be great, so let's see. If I push graph in the top right corner, we'll get that. And I want a little bit of a better picture, so what I can do is I can click zoom on the top middle, and I want to set it to zoom standard, because that usually gives me a 10 by 10 window. So let's try that. If I push enter now, great. So maybe on my graph that I drew, my arrows are a little wide. Maybe I can make it a little more narrow, but other than that, I got the general gist of what the graph looks like correct. So I think we're good to go there. I went ahead and I changed my graph to try and make it look a little more accurate. Okay, definition. If c is a zero of a polynomial p and the corresponding factor x minus c occurs exactly m times in the factorization of p, then we say that c is a zero of multiplicity m. So why do we care about the multiplicity of a zero, or in other words, how many times a zero is showing up? Well, it turns out that it's going to tell us the shape of the graph near that zero. So let's start off in this table. If we have a zero that is positive and even, then the graph near that zero is either going to look like this or like this. So in other words, it kind of touches the x-axis and then bounces back. If we have a zero and its multiplicity is odd, then that means the graph is going to go through the x-axis and look either something like that or something like that. So can we think of some examples? Well, let's look at y equals x minus 2 quantity squared. If I were to graph that, from my parent function y equals x squared, our vertex and every other point would shift right 2 units. So here's 2. And because our 0, if I plugged in 2, that would give me 0. So our 0 is 2, but it has a multiplicity of 2, which is even. So that means that our graph is going to touch that 0 and then bounce back. And it's going to look like that. So same idea. Let's say I erased this power, and let's say it was x minus 2 to the 6th power. It would still look something like what I've drawn, just slightly different, but it would touch at the 0, and then it would bounce back because this multiplicity, or our 0, is 2, and it has an even multiplicity. Example 6 says sketch a graph of the function p of x is equal to x to the 4th power times x minus 2 cubed times x plus 1 squared. So this is nice because it's already factored for us, and what I want to do is I want to make a little table that tells me what the 0 is and then what its multiplicity is. So this factor here, x to the 4th, if I were to set that equal to 0, then I would get x equals 0. And because the power on that is 4, it would have multiplicity 4. Then in my next factor, which is x minus 2 cubed, if I set x minus 2 equal to 0, then we'd get that x is equal to 2. And the power on that is 3. So the multiplicity of that 0 is 3. And then in the last one, we have x plus 1 squared. If I set that equal to 0, I would get x equals negative 1, and its multiplicity is 2. So this is going to help me graph because I'm going to plot my x-intercepts, which are 0, 0, 2, 0, and negative 1, 0. The other thing that I can try to figure out is the end behavior. So even though this is in factored form, if I were to expand this polynomial, because this is x to the 4th, and then I have x here and x here, and if I were to expand this, I don't need to multiply everything out. I would just need to recognize that if here, let me write this out. So I have x to the 4th times x minus 2 times x minus 2 times x minus 2 times x plus 1 times x plus 1. So if I were to use the box method or the FOIL method, the first thing that I would need to do is I would need to multiply this thing with this, 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 and this. And because those are all x's, my very first term, assuming that I'm writing these in descending order of power, is going to be x to the 9th power. And the way that I can get 9 is I can just add up these exponents. So I can add up 4, 3, and 2, and if I add those up, I get 9. So we have x to the 9th power is our leading term. So our degree is odd, and our leading coefficient is positive. So that tells me that my end behavior is going to be down and then up. So it's going to look something like that. Now, our negative 1 has an even multiplicity. So this is even, which means when I'm drawing my graph, it's going to bounce back. And then my next one is also even. X equals 0 has an even multiplicity. So I'm going to go and then I'm going to bounce back. And then finally, at x equals 2, that multiplicity is odd. So my graph is going to go straight through. And it's going to look something like that. Now you might be asking, how did I know how low to go here? How come I didn't go lower here? I actually don't know that answer. And really what's happening there is we have local minimums or local maximums, and we don't have the tools to find where those are yet. And you will, though, once you reach calculus. But right now we don't have those tools, so I'm just giving my best guess about how low to draw those. I call them valleys in my class. I call them peaks and valleys. So when I'm drawing a graph, I refer to that as a peak and then this as a valley. So this is a peak and this is a valley. So again, you might be asking, how do I know how low to draw my valleys or how high to draw my peaks? I don't know. I'm just giving my best guess because right now we don't have the tools from calculus. Here in example 7, we have a box and we are going to create a tray by cutting out square corners. So part A says identify an appropriate restricted domain. Well, our input value is x, and here x represents the length that we're going to cut out from each corner. So because that's the case, if this is 12 inches and this is 14 inches, if I were to make x 4, that would be okay because I could cut out 4 from this side and I could cut out 4 from this side. But I wouldn't be able to cut out larger than 6 inches because let's say I tried to cut out 7 inches here and 7 inches here, that would total more than 12 inches. So to answer part A, the domain would be anything from 0, so that would mean we would not cut anything. And then the most we could cut out is 6 inches. So there is our domain for part A. Part B says find the volume of the box as a function of x. So I want to create a function. I'm going to call it v of x, and it's going to tell us the volume of this tray that we create right here. Now, if you don't know, this is called a rectangular prism, this three-dimensional shape. And the volume of a rectangular prism is you multiply these 3 dimensions together, the width, the depth, and the height. So I'm just going to go ahead and write those words out. The volume of this tray is going to be the width times the depth times the height. And I want expressions for each of those things. So let's say that the width is here. And if I'm cutting out x here and x here, that means that the width of my box is really going to be from here to here. And the way that we calculate that is 12 minus 2x, because I'm cutting out 2 different corners there. Now I want an measurement for the depth. So I'm starting out with 14 inches, but I'm cutting off a corner here and a corner here. So really the depth of my tray is this dimension there. And similarly, that's going to be 14 minus 2x. And then after I folded these up, my height here is going to be this value here, which is going to be x. All right, part C says use a graphing calculator to graph y equals v of x and approximate the dimensions of the box with maximum volume to 2 decimal places. So I have a graphing utility, and I'm just going to quickly sketch what the graph looks like. So here is v of x, and here's x, and this is a cubic polynomial because I have factored it into 3 linear factors. There's a 0 here at the origin. There's an x-intercept here at 6. And then there's another x-intercept here at 7. And because it's a cubic and the leading coefficient's positive, it's going to look something like that. Now, something to be mindful of is that we originally stated that our domain is between 0 and 6. So I'm actually going to erase this. And really, our graph looks something between 0 and 6, looks something like that. And we're stopping there. So we want to figure out this point right here to figure out what x value is going to give us the maximum volume. And I'm just going to state the value since I have my graphing calculator here. And if I'm rounding to 2 decimal places, this is going to be 2.15. And then my output value is going to be 160.58. So if it's asking about the dimensions, then here is x. So the dimensions that would produce the maximum volume would be 2.15 inches by, and then if I plugged in 2.15 for x here, and we calculate those, that's going to end up being 9.7 inches by 7.7 inches. So these represent our width, depth, and height, not necessarily in that order. And then part D says, what is the maximum volume? And so that's V of 2.15. And we said here that it's going to be approximately 160.58. And because we're measuring volume, it would be cubic inches. And that's our answer for part D.